You're listening to the Silicon Valley Podcast.
On today's show, we sit down with Axel Kloth, who is a physicist by training, and he is used to the need for large-scale computing. Axel discovered over 30 years ago that scalability of processor performance was paramount for solving any computational problem. That necessitated a new paradigm in computer architecture at Parimics, SSRLabs, and Axiado. He was able to show that new thinking was needed and what novel practical solutions could look like. He's now repeating that approach with Abacus Semi. On today's show, we talk about what is an application programming interface, an API for short? Why do we need APIs? Are there legal issues on use and modification of APIs? If you were in school right now studying computer science, what would you want to learn and why? And where will the industry have the most problems in the coming year?
Welcome to the Silicon Valley Podcast with your host, Sean Flynn, who interviews famous entrepreneurs, venture capitalists, and leaders in tech. Learn their secrets and see tomorrow's world today. Axel, I want to thank you for taking the time today to be on the Silicon Valley Podcast with this joint partnership for this event today. With that, our audience at home, everyone loves tech, everyone loves venture capital, everyone loves the startup ecosystem here in Silicon Valley. So to start with that, can you give everyone a little bit of a summary of your career up until this point?
Yes, sure. I'm a physicist and computer scientist by training, and I started my career at Siemens in Germany, where I was the usual renegade that I am. So I got hired to do testing, and that bored the living daylight out of me. And so I developed a system that tests for me. And so instead of me hacking away at testing back then, EWSD, if all of you remember the plain old telephony system, the pod switches, class 4 and class 5, too boring to test. So again, I developed a test system with two co-conspirators, without any permission from the bosses. And it worked out well. It worked out, in fact, so well that I nearly got fired over it. But at least it tested very well, and it created a business unit that about 15 years later was sold for about $100 million. After that, again, and I think you would see a common theme. I get bored easily if I do the same stuff for too long. I was assigned to design processors for the Siemens, or back then Siemens Microelectronics that became Infineon, for all kinds of network products that were not supposed to be ATM or telephony systems. I did that for about 2 years, got to a point where we had, in fact, quite a few processors taped out that were about to be introduced when Infineon lost its guts and basically said, yeah, stop doing it. After that, I lived for a company that was called Hot Rail. They were focused on making a switch fabric, a CC NUMA switch fabric for EV67-based buses, DEC Alpha and the AMD Athlon MP. Taped out the product, worked, and then both processors were withdrawn from the market. So we had a product and nowhere to go. And I was brought on to fix that. So we recast the switch fabric as a switch fabric for communications, made the first and only combined virtually output Qt switch fabric happen. Also developed a new technology for transceivers, high-speed SER links. Instead of LVDS-based, they were CML-based. And we beat the incumbent by a factor of 3 in terms of throughput and a factor of 3 in power. And then again, I got bored and started something else. And I think that's a theme by now. When I got bored, I started something else. So that was intended to be a vision processor company, image processing, called Parimics. That was in 2004. And by 2005, we had everything to be able to support autonomous driving. So basically ADAS, advanced driver assistance systems. And the comments from VCs I got back then was, nobody wants to do that because everybody enjoys driving. I said, well, I'm not so sure about truck and bus drivers. They certainly would want some help, and they would prefer a system that helps them in case things get messy. And we did that until about 2011, and that never took off in terms of funding. So I stopped, briefly joined a company where I introduced a system that consolidated all of their engineering into a single system, worked out incredibly well. And as soon as it worked, first of all, I got bored and left. I think you see a theme here. And then I started a company called SSRLabs based on scalability. And, most of that is I'm resuming now with Abacus. And I'll get into it in more detail if you're interested in that. But I did that for a few years. And this time I didn't get bored we got a private request for a proposal from the Department of Defense and Department of State to develop a secure processor. I did that, spun it off as Axiado, and as of now, that company is in business and doing still something else. But then again, I got bored. What else could you think? So then I left and started this company, Abacus Semiconductor.
Okay, so for the next 1 to 2 years before you get bored, I got to ask, Abacus Semiconductor snapshot, what's the problem and the use case that you're solving until you solve it and get bored?
The use case sounds very theoretical and hypothetical, but it's not. My assumption for the last 15 to 20 years has been that we live on a beautiful planet and we do everything we can to ruin not the planet, but our ability to survive on it. And so my lemma, my theorem has been for those 20 years that before we do something, we better simulate the living daylight out of it. Because if we make an experiment, we conduct an experiment and it backfires, maybe by that point in time, it's too late to make sure that humans can survive on this planet. The planet will survive and cockroaches will survive. Whether humans can survive on this planet, that's all up to us. And I want to contribute to the fact that we can simulate everything we do before we actually implement it. And so that's why I'm focusing on this, where I'm saying we can not give away, but we can give scientists who want to do simulations for all kinds of things, even using if this then that. We want to give them the opportunity to buy a desk-side supercomputer for $250,000 instead of $100 million that can solve the question of, if I simulate this and I have a positive outcome, can I suggest that we do this because then humankind might survive on this planet? That's what drives me.
I mean, that's a noble goal. So maybe it'll be 2 or 3 years before you get bored.
Let's hope so.
The topic of the conversation what is an application programming interface, or an API for short? I mean, let's just go right into it.
Right. So one of the reasons I wanted to do what I just explained was it's needed. And we've made multiple approaches so far as a community and as the technology industry to solve this problem. But most of the time, the approach was on somebody just using more software on existing hardware. And that didn't solve the problem. I think by now, every scientist in computer science has recognized that we need accelerators. And the accelerators now pose a different problem. They are pretty damn good these days, and so are processor cores. But the cores have to talk to the accelerators. And that is one of the many things that is done by what is called an application programming interface. So you have a driver to make use of the accelerator or the device out there. And then you've got an API that on a higher level connects whatever you want to do and want to simulate to the driver and the accelerator. So it fits right into what we are doing. And that's why I volunteered to give this talk, because I think there's a lot of confusion on what really is an accelerator, what is an API, how do they play together, what could prevent them from playing nice together, and what APIs are out there, is there some legal issue and all that kind of stuff. But we'll get to all of that.
I like how you just summarized every question I'm going to ask. So question right there. I mean, you talked about APIs and communication. Can you give us an example of an API?
Yeah, there are plenty of APIs out there today, and the most widely used API in the industry probably is an entire collection of stuff that's hidden in a proprietary API called CUDA. And CUDA is effectively a proprietary version of a collection of routines that scientists use for all kinds of math routines, for artificial intelligence, And NVIDIA has developed it, NVIDIA owns it, and NVIDIA spends a lot of money on paying developers to advance CUDA. So CUDA itself is an acronym, it's an abbreviation for Compute Unified Device Architecture. To the credit of NVIDIA, they spent a lot of money making it and making it available, right? And so that's, of course, a good thing that's available, but it's proprietary.
Can we go back even a little bit? I mean, there is so much information there. Can we just go back to, why do we even need APIs?
Again, strictly speaking, if we just go to the definition, APIs it says application programming interface. So it's an interface that connects one application to another application. And usually it connects an application on the higher layer with an application on the lower layer. And if you look at the entire stack that there is, you've got hardware consisting of processor cores and accelerators if they are present. Then on top of that, you've got an operating system. The operating system has a kernel. There are drivers needed for the accelerators or GPUs. In today's world, mostly GPUs, right? The drivers make it possible to use the device at all, but that's usually not enough because ultimately nobody wants to rewrite something like a matrix multiplication. So those are the higher layer applications in the API that are made available by the API and then can be used by the higher layer software that you are writing to simulate something or to do a crash test and all that kind of stuff. But again, I mean, there are multiple there are multiple definitions of what an API is. And, I'm reading one from MuleSoft. And so they say API is an acronym for Application Programming Interface. And with that part, I agree, which is a software intermediary that allows two applications to talk to each other. No, not terribly correct. Right? But that's unfortunately a definition that's oftentimes used. They also claim each time you use an app like Facebook, you send an instant message or check the weather on your phone, you use an API. Well, in a way, yes, but that's not really, terribly useful because APIs are vastly more than just this. So to me, that's not a very useful definition of an API. Let me give you an example of what I believe is a much better description of an API, and then we can get into what a definition of an API is. So let's say I'm developing software or hardware, doesn't really matter, either one. So now let's say strictly and purely hypothetically, I found a new way to execute the square root function. It's used a lot and nobody wants to spend any time to refine it. Let's say I find a new way to do that. So what I'm doing is I write the software that executes the square root function. And of course, I want everybody to use the square root function, not steal it. So what I'm going to do is I'm compiling the square root function, and at the same time, I'm now defining what the call parameters are. Everything that you need to put in, the function name, and everything that comes out, including, of course, the format of all the data, whether it's integer, floating point, unum, posits, whatever, and their respective lengths. I have to define that because if I don't, then you as a user of my API don't know what the format is, and so that would be bad. So as a result, I need to be able to not only compile the function that executes the work, but also I have to give everybody an interface so that they can use it, and I have to exactly define what the parameters are that are handed over to me, and then what I hand back to you. And so that's really what an API is if you boil it down. That's a function call. Of course, if you look at math libraries today, there's more than square root, there's sine, cosine, and. There are hundreds of those. And of course, most people would get bored if they had to rewrite all of that kind of stuff. So therefore, it is incredibly useful, and it's a lot of code reuse if an API is available, so nobody has to rewrite all of that stuff again. That's really what the benefits are, and that's what they convey and what they do. The good thing of an API is if I write this as software or if I invoke a particular function on my hardware, then I don't need to disclose what is happening sort of as the inner workings of the API. You as a user don't care for as long as it works and as long as it's fast and gives you the correct results. You don't care what I do inside my API. You just call it, it gets you back the result. And if you're happy with the result, you keep using it. And so over time, I will expand the library of functions I have. So my API, the APIs are getting bigger and bigger, and hopefully more and more broadly used, right? So that's really my part of it. And that's something I can keep a secret because the code is compiled. And unless you take a disassembler, you don't know how I get from A to B, from your input data that you hand over to me to the output data that I hand back over to you. That's a benefit to me. I've written it, I've compiled it. It's not really visible to anybody what the inner workings are without them decompiling it. And if I use hardware, it's even better because, well, unless somebody really wants it, decompiles the instructions of everything and then sees what I hand over and maybe figure out how the hardware works. But that's usually too much work. So usually people don't do that. They say, oh, great, there's this wonderful new API with the function I need. I invoke it, it works, everything's fine. Everything's hunky-dory, right? And I don't have to disclose anything of the inner workings of my API. Therefore, the inner workings of the API should be patentable, and they should be, in a way, protected. They have to be protected so that nobody can just go ahead and steal them. I want everybody to use them and possibly pay for them, but I don't want anybody to steal it. And so that's part of what makes it so attractive. So it's in a lot of ways code reuse without you knowing what exactly the code does. That is a big benefit of the invention we've had with the APIs. And so the good thing is, of course, if somebody comes up with a better algorithm for a square root function, well, guess what? They can use that and they will displace me over time, which, of course, is possible, is perfectly legal. But what I want to point out is, let's say I call the function sqrt. And if somebody else calls that function sqrt, I should not be able to patent it or trademark it because it's an abbreviation for square root. Square root is a mathematical function to which I have no right. I have a right to an algorithm, but I don't have the right to the mathematical function. So if I have a better algorithm, all great. I don't own the name of the function and the function call sqrt. I just don't own that because I shouldn't be owning that. And so if you go back to, for example, the recent decision of the Supreme Court of the United States, they just had a case decided, which was Oracle versus Google. So Google had used Java function calls, which was perfectly legitimate. And that was, in fact, intended. And then Oracle came back and sued Google for use of those functions. And, luckily, the USPTO and the Supreme Court decided, no, sorry, not patentable. You have no case. That was the entire purpose. Therefore, the use of an API shouldn't be patentable. The name of an API shouldn't be patentable. What can be trademarked and patented is all of the inner workings of the API, but not the function call itself. So if somebody, let's say I have a beautiful library full of stuff, and somebody else develops something that's better, well, tough shit, right? Either I have to make mine better, or I'm out of business if I sell them, right? It's really as simple as that. So that's a little bit lengthy, and it's not quite a definition of an API, but in essence, an API is a collection of function calls from a higher layer piece of software into something lower layer that executes and facilitates code reuse.
So you might have already answered this, but what would an ideal API be?
Well, the ideal API is free. So basically free of cost, free of royalties. And it executes all of the functions that I need. And it's easy to use, and it is free of bugs. And it's hopefully as fast as anybody can make that algorithm executed on the target machine, which of course by itself is bifurcating many, many times, because again, target machine in my case could be a computer that only has CPU cores, but it doesn't have an accelerator. On somebody else's machine, it may have CPU cores and an accelerator. So it all depends on, to some degree, what the target machine is and what the situation is on that machine with regards to, how much memory does it have? Does it have accelerators? And. So that's why my company, we are focusing on a very specific set of functions we execute on those accelerators as fast and with as little energy as possible, scaling out over hundreds of thousands of cores.
Now, can you talk about the accelerator, just that term accelerator? I mean, most of the audience here, they know about accelerators and incubators and that, but maybe not in terms of with APIs.
Right. So accelerators usually are not the accelerators that very likely you are used to. So it's not, the equivalent of an incubator. An accelerator is a programmable or a fixed function device that supports the host CPU in executing a very specific function or a set thereof, ideally autonomously, right? So in other words, let's say you always execute, sine functions, right? So, or cosine, doesn't matter. So what you want is, of course, now a library or an API that says, hey, on my machine, this sine function always creates the fastest response. It's always correct. And it never causes any trouble, right? Well, that's sort of ideal. It doesn't exist, but ideally, right? So that's what we want. Or square root. It doesn't allow you to do square root on, negative integers or stuff like that. It says, sorry, error, right? Well, we can do the imaginary part of it too, but that's a different story. Again, so an accelerator is a hardware piece that is added to a processor in your server or your desktop, whatever. It's something that offloads the CPU from doing nasty stuff that CPU designers never want to design. Again, plenty of examples. The simple ones are square root, sine, log x, cosine, whatever. But then there are ones that are much, much bigger than just, a single function like sine or cosine. So usually when you look at benchmarks, all of those bigger machines, supercomputers, are benchmarked using something that is called SGEM, DGEM. So they are matrix multiplication or Fourier transforms. All of BLAS, for example, is basically linear algebra systems. All of those functions, they require accelerators so that they accelerate the execution of this stuff in a reasonable time frame. Because ultimately, you want your result in your lifetime. If you get the result after you're dead, you don't really care much more about it.
Axel, I have a quick question for you, and this is probably going to make me sound very intelligent, but I'm not sure. Can it be thought of as a load balancer?
Well, load balancers by themselves are accelerators. So yes, correct. Load balancers are accelerators because ultimately the idea, of course, of a CPU today is, let me try an analogy. If you're the boss and you got 20 people working for you, you are not doing the work. You delegate the work to 20 people. So in a way, now you are the load balancer. As a boss, you are the load balancer because some people are better at this, other people are better at that. Some people are better at staying home, and some people are better at getting shit done. So your job as a boss is to balance the load onto those that actually get shit done and that don't prefer going home. That's what you do. So you first find what is the capability of that employee, and then you put as much load on them as you can because otherwise they'll get bored.
And then start another startup.
Exactly.
So Axel, another question for you. Why does it seem like it's so difficult to get an accelerator and an application software to talk to each other in a meaningful way?
I asked myself that question 15 years ago, and back then I didn't have an answer to that. Today I do. I've written code in all kinds of languages. I stopped counting how many languages I use to code stuff. But if you have a look at any kind of an accelerator, including a load balancer, all of them are basically hardware pieces, and they consist of a register that takes data in, a register that spits data out, and a register that is input for the command, and a register for output of the status. Usually, when you give that info of registers to a programmer that dabbles in high-level languages, Fortran, COBOL, whatever, or Python, my current favorite object of hate, if you give those people the description of registers, they will run. That's all they're going to do. So what needs to happen is you have to have somebody with enough patience to write a driver that in fact can talk to this accelerator, whether that's a load balancer, a math processor, or a database accelerator, it doesn't matter. You have to have a driver that lets the CPU core talk to that accelerator. That is a piece of software. You're still stuck with so here's the parameters that I hand over, and here's the stuff I get back. It is not seamlessly integrated into any kind of high-level languages. So for that, you now need another layer that says, okay, here are all the damn functions that this accelerator can execute, and please look at the format. And for as long as you fulfill the requirements for the format, the calling parameters, and how you get the data to the accelerator and back, we're good. You get results. So this now becomes usable to programmers of any high-level language. So you've got the driver, which is a kernel mode thing. And then you've got the API, which usually isn't a kernel mode thing. And then you've got your application that calls into the API. So it just makes life a hell lot easier for the programmer, dabbles in any kind of a high-level language. For assembly programmers, it doesn't matter. They don't care, right? In fact, they probably would prefer not to have any API and this and that in between because they've got much better control over the hardware. But then again, most people today don't code in any kind of language that is close to the hardware. For the most part, if I try to look for people who are, and I call them C with the assembly language knowledge and, willing to do low-level stuff on register level, usually they run. So for the most part, the issue today is you got a driver, you got an API. On top of the API, you got plenty of happy people using it.
Okay, so next question, do accelerators always accelerate? What could go wrong, and when's that the case?
Yeah, so despite the fact that they're accelerators, not all in all cases, do they accelerate program execution? And let me give you an example as to why that might not be the case, which is, of course, why the load balancer and a whole bunch of other things are very important that you need to know. And that's, of course, why also usually an API is good enough to figure out what happens and whether that accelerator accelerates your execution or not. So let's say you've got a problem that on the CPU would require about 1,000 cycles to execute. Now, let's say you also have an accelerator that only takes 100 cycles to execute the same function. Then you would think that in every single case, it's good to use the accelerator. Okay, let me tell you that that's not the case. The data oftentimes has to be copied from user space to kernel space, which takes a whole bunch of cycles if the CPU has to do it in software. So first of all, you have your API function call. So you hand over something. Then you hand over data. Then you tell the accelerator through the API and the driver to execute its thing. It executes it. And then it alerts you, hey, I'm done. I got the result. Usually it does that through something called an interrupt request. So it interrupts the CPU in its program flow because the purpose of outsourcing something to an accelerator, like the boss having the employees do the work, is the boss can do something else. Whether that's productive or not is a different story, but it can do something else. So let's assume the CPU has decided to do something else that's useful. It then gets interrupted because of the interrupt request in its program flow. Now it has to branch into what is called the interrupt service routine. The interrupt service routine now deals with the interrupt coming from the accelerator saying, hey, I got the data. So now the CPU gets the data. Well, but of course it can't directly do it because now we have operating systems with protection so that only sophisticated thieves can get to data. So the data now needs to get copied again from kernel mode to kernel space to user space. And if you add up all of those cycles, you will find that's easily 1,500 cycles. All of the mechanics of calling into the API, into the driver, then running the ISR after the interrupt request has been received, can be more time than it would have taken to execute that function in software. So in that case, you have used the CPU, you have used the accelerator, you have used power for both, and you've made it slower. So that was not terribly useful. So therefore, it is always important to have a look at how much do you accelerate by doing something that is a relatively short thing. And most accelerators today, they are predicated on handing them gigabytes worth of data so that the CPU core can do their thing, the accelerator can do their thing or its thing. And then after, hundreds of thousands of cycles, they say, hey, I'm done. So in that case, it will accelerate. But in the case of, 1,000 cycles worth of stuff, don't do that.
And with all the APIs out there, which ones should we know about?
Well, that of course largely depends on what you're doing, right? So if you're purely focused on math, then OpenCL is probably good enough. If you do math and you subscribe to the idea of a captive proprietary API, then very certainly, CUDA is a very good choice. And if you use any kind of AI today, I have yet to see anything that's not predicated on CUDA. AI basically says you have to use CUDA. Whether you like it or not, you have to. OpenCL is OpenCL together with OpenACC is probably the alternative choice if you do a lot of math and you must stay in the open source realm. Or let's say you have your own accelerator. So let's say you have a very special function that you have developed that you put onto an FPGA. FPGAs are not supported by CUDA. CUDA supports NVIDIA GPUs. If you have a problem that you need to solve, let's say on an FPGA, or if you've got an AMD GPU, well, guess what? You're confined to OpenCL and OpenACC, possibly even using OpenMP for load distribution on it. So it really depends on what you want to do and what your tolerance is. And I'll come to some degree to the economics of using open source versus closed source. But it depends on the application, on your higher level application that you need to support and then you need to write. And how much time do you have and what's the team size? Lots of considerations that you need to take into account when and if you choose your accelerator.
I like how in this conversation, when you're looking around, you think everyone here in the room knows everything you're talking about. I like being included in this. Like I'm sure at that level. So thank you. So can we go about maybe one, I want to dive deeper into CUDA, but even before diving in, get into, the nitty gritty, you'd mentioned something about kind of legal issues. And I was wondering about legal issues and use and modifications of APIs.
Yeah, so that's part of the thing that I already brought up, but there's a little bit more to it. So most of the APIs that you find are written with a specific license that is very and fairly permissive. So it basically, for as long as you attribute the underlying API to the authors, you're good. That would be licenses like BSD and MIT and all that kind of stuff. These licenses are permissive. You can use them. You don't have to pay any royalties. And you can do with the code what you want. So the resulting code can be turned into closed source, or you can open source it. Now, sometimes there will be a reason why you want to keep things closed source. Let's say you use an open source API like OpenCL, OpenACC, and you compile that with a compiler that is not GPL, that is, again, a BSD or an MIT license. Then that code can be made closed source for as long as you attribute all of the components where they came from. And then you're good. So let's say you have developed a special purpose XYZ thingamajiggy that you run on your FPGA, and you don't want to divulge how it works. In that case, keeping the resulting code closed source makes sense because somebody disassembling and reverse engineering your code could find out what the FPGA does. And of course, you don't want that because let's say you spent 2 years and 4 people on it, 8 man years. So you're talking a good $1.5 to $2 million. you don't want to give $1.5 to $2 million to the open source or to any community because you spent that money and that's your distinguishing element in that application. There were lots of companies doing this, particularly for oil and gas exploration. And it was a multi-million-dollar business, and they did that on purpose, and they kept it closed source. So I totally understand why certain things need to be kept closed source. And that's why certain licenses are permissive and you can use them. Other licenses are less friendly. Other licenses, such as GPL, they will require you to open source whatever is predicated and based on anything, even the teeny tiniest little bit of their code. And that's why we do not use GPL. We don't use any GPL code in-house and for any of our products because it would require us to open everything up that we have developed based on this. And we can't afford that because, last time I developed a processor and we got it on the cheap. It was $20 million. And there were $20 million worth of secrets in there. And that's, as I said, that was at a discount. Usually the industry assumption is it takes you about $100 million to develop a processor. So if you develop a processor, even if it is just something you implemented in FPGA, and even if it is something special purpose, you may need to keep that secret because you can't afford all of that to be dispersed.
You should have asked her FPGA.
Oh, a field programmable gate array. It is an ASIC that is not quite empty. It consists of 6 input lookup tables, 6 input LUTs, gates. And this FPGA can be programmed to do pretty much anything that there is. It can emulate any function. It can emulate any fixed function device. It can emulate any kind of a gate. It can emulate even a processor with its pipeline and with its execution units and. So that's what an FPGA is. The biggest FPGA providers are Xilinx, Altera, that is now part of Intel, and Microsemi. But if you have a project that doesn't run fast enough in software on its CPU, and you can't afford to build an ASIC, then an FPGA is a very good in-between solution to solve that problem because it gets you very good performance, much, much better performance than a CPU software. It's not performance-wise quite up there where, a special purpose ASIC would be. But then again, that's not going to be $100 million.
Okay, what about captive APIs?
Captive APIs, that again, that's a piece of math you have to do very likely with your director of engineering, sometimes the VP engineer or CTO, because sometimes there is a case to be made for captive APIs. So if you want to use CUDA and it cuts your software development time in half, and I have that somewhere here, we can get to the execution flow as well. But the idea is, of course, every single time you develop something that you get it out to the market at a time at which there is still demand for it. If CUDA as a captive API allows you to get the project done in the allocated time frame with the allocated resources, then you're good. Even if it means that you have to buy lots of NVIDIA GPUs. Even if it means that your customers can run it properly only with decent performance if they themselves buy NVIDIA GPUs. But the fact that you have cut your development time and allows you to capture the market might very well be a good enough reason to use a captive API. In some cases it will be, in some cases it won't. It all depends on how much time do you save using a captive API versus an open source API. And I think I alluded to the fact already that CUDA, while captive and closed source, is incredibly broad. It has an incredible breadth of functions and makes a lot of stuff available that otherwise you would have to either develop yourself or buy from other providers that buy into the idea of open source like OpenACC and like OpenCL.
Axel, what else should we know about CUDA?
Well, again, CUDA is a project that NVIDIA started probably close to 20 years ago. It's very comprehensive. It is very well tested. It works extremely well. And it is basically it's a lingua franca of APIs when it comes to math and to AI. There's really nothing else out there like CUDA when it comes to these groups of applications that you may want to tackle if you have a commercial software project that you're developing for a customer or in-house.
Now, you had mentioned NVIDIA 20 years ago. What happens if you have a legacy code that no one understands? Isn't that kind of what happening in fintech and the banks right now? I'm just wondering.
Correct. So CUDA has the advantage of being broad and having been around for a while, and it's highly unlikely to assume that it will go away. And in fact, despite the fact that I don't particularly favor captive APIs, a wide variety of applications, there's no way around it. You have to use it, right? And there's nothing wrong with that. Because ultimately, if you look at things that used to be the programming language du jour, it could be Fortran, it could be COBOL. There are lots of projects that have been started, 30, 40, 50 years ago that today can't be maintained because the language isn't prevalent anymore. There are basically no more programmers for it. And the knowledge of the language and all of its implications has gone away. It is less likely that something like that would happen to CUDA. Fortran programmers, where do you today still find Fortran programs or programmers? It's only in the scientific world, right? You probably find them at Lawrence Livermore National Labs. You find them at CERN. You find them in very, very specific applications and industries. That's where you find Fortran programmers. COBOL programmers used to do everything in banking. So if you have a mortgage application, it's 99.9% certain that the mortgage was computed with a piece of COBOL software. Because of the fact that back then compute wasn't quite as pervasive, and because of compute being relegated to a much smaller pool of programmers, when those programmers retire, the knowledge goes away. And so the only hope is that, in 3 to 5 years, we have trained AI well enough that it can autonomously rewrite COBOL and Fortran programs into C and C++. If that doesn't happen, we will have a very rude awakening when the hardware that runs COBOL and Fortran goes away and becomes obsolete, and we can't find anybody to rewrite that software. Then nobody can, well, I'm going to say nobody, but then the issue of figuring out how to get your mortgage application resolved with a provably correct result, that's might go away. CUDA at this point in time is large enough that that's not going to go away.
So I'm kind of curious right there. I mean, you said mortgage as the example a few times, but where do you see potential problems lying ahead? What industries? Where should we be concerned?
I think you will see that throughout the entire industry, all of those areas where you had the need for a specialization and a very, very short talent pool, where those were prevailing, that's where we're going to see the biggest problems, right? And I think the two biggest problems are going to be COBOL and Fortran. Because, at some point in time, these people will retire. In the next probably 5 years, they will retire. And after that, there will not be many COBOL and Fortran programmers left. And had we taken the step to convert all of this over earlier on, 10, 15 years ago, onto either CUDA or OpenCL or OpenACC, I don't really care either one of them, we would have a whole lot less of a set of problems than we will have in 5 years when all of the guys with the gray hair retire. well, guys and girls.
So then to continue that question, if you're a student right now studying computer science, what should you be studying?
I think the issues is more of what you're interested in. If you think that you like hardware, then yes, do computer science with electrical engineering. You will still have a hell lot of fun, because whether we are still designing digital chips in 5 years or 10 years, or whether we're going to do anything, quantum compute, I think you will have a lot of fun doing that, right? There will be plenty of demand for it. And I think there's a lot of learning going on and a lot of training. And I think there are a lot of people who are interested in teaching that you wouldn't easily, get bored and become unemployed. That's one thing. The other thing is if you feel more like you're more suited to software and higher layers and to the more abstract level, then my suggestion would be try to figure out if you can make yourself comfortable with the concept of AI, not the current implementation of AI. There may be things that we completely turn around and change again in the next 3 to 4 years with the underlying hardware for AI, both for training and for inference, and for everything that is based on the current prevailing idea that Python on TensorFlow on CUDA is a great idea. But if you can get yourself to the notion to actually like the abstract concepts of AI, I think that would be something that will have a future independent of what the specific implementation of inference and training is going to be.
I got one more question about the future before we start wrapping it up and opening up for Q&A for the audience. Got to be respectful of everyone's time. But I mean, speaking of the future, why still focus on developing digital processors when quantum computers are going to come around and just kind of blow them out of the water?
Yeah, we, of course, had to ask ourselves that question as well. So my answer to that is quantum computers do certain things very well. Google has proven for certain applications quantum supremacy. There's no way that a traditional processor can even remotely compete with that. There's an entire class of problems that run extremely well or will run extremely well on quantum computers. Once we get past the current limit of, I think, 57 qubits is what we have. So once we're past that, there will be not only one, there will be classes of applications that simply wouldn't be worth running on any traditional computer. It wouldn't make sense. However, I believe that there are other, and in fact, I think the number of classes of computational problems that are better solved on a traditional processor, they will persist to exist. And I think the number of classes is larger than the number of classes of compute that should be executed on quantum computers. So I don't think it's an exclusive or. I don't think we either have the traditional processors with accelerators or we have quantum computers. I think we will see that a vast majority of the problems will still be solved on, not quite traditional machines, but the machines that are more resembling what we are developing. And then there will be the quantum computers that solve problems that are not ideally solvable on von Neumann machines or even Harvard machines or whatever you want to call them. It doesn't have to be even SIMD, VLIW. I don't want to throw any more acronyms around here, but there are classes of problems that run very well on traditional machines that really don't execute too well on quantum computers.
Well, Axel, we've already had our first question from the audience, so we'll dive into that right now before opening it up to everyone on Zoom. What are your thoughts of AR, augmented reality, and blockchain technology?
Okay, so AR may be an issue of, I think, personal preference and how how well your brain is connected to the three biological instruments that keep your balance, and I forgot what they're called. My experience with AR is I simply get dizzy. So whether I have, a projection of something large scale with a latency that is perceivable, and then me taking action, and the action is always delayed by a constant amount, makes me dizzy. So it could be that AR might work for people who are more capable of making less strong of a bond in between what they think the expected response of the system is and the actual response. So if there's less of a correlation, then maybe they fare better than I do, but it didn't work for me. Blockchain, well, let me put it this way. A lot of people misunderstand what blockchain really is. Blockchain is a very neat way for effectively a distributed ledger that can be proven by everybody and anybody that certain transactions happened. So you have a traceability and a provability along the path of transactions. That by itself is useful. Whether I would use that to create virtual money, that's a different story. That is up for discussion. Yeah, blockchain by itself is an interesting application where theoretical math has proven to be very useful for proving that certain transactions took place.
All right. I threw that curveball there at the end, but just for respecting of time, we're going to open it up to questions on Zoom. But Axel, let's wrap this up. If anyone wants to find out more information about you or what you're working on for the Silicon Valley podcast audience, what's the best way to go about doing it?
The best way is to either email me or, there's the contact info is on the website, but it's axel.kloth, axel.kloth at abacus-semi.com. So if you got any questions, I'd be more than happy to read them, to try to understand them, and hopefully be able to answer them.
All right. And Axel, I want to thank you again for being on the Silicon Valley podcast. And I really want to thank Nikki and the team for putting this joint event together. And now let's open it up to the audience.
Thank you. Great.
Thank you for listening to the Silicon Valley podcast. To access our resources, visit us at thesiliconvalleypodcast.com and follow our host on Twitter, Facebook, and LinkedIn at Sean Flynn SV. This show is for entertainment purposes only. Before making any decisions, consult a professional.